Here is the counterintuitive part of orbital solar power. The hard problem is not collecting sunlight in space. The hard problem is delivering controllable, governable, economically defensible power after everything goes wrong. As of 2026, no operational system delivers sustained, grid-scale, commercial electricity from orbit to terrestrial grids. The field is still a mix of studies, subsystem work, architecture definition, and limited demonstrations. That gap matters because most designs look plausible on a diagram. Very few are measured end-to-end as a coupled system. Start with the oldest and still most binding constraint: heat. In vacuum, you cannot dump waste heat into air or water. You have to radiate it away. Engineers identified waste heat disposal as central all the way back in 1959. That early insight still sets the mass and size of real systems today. Radiator temperature, surface area, coatings, and long-life durability become primary design variables. If your radiators grow faster than your delivered watts, your concept quietly collapses under its own mass. High-temperature conversion sounds like a solution, but it tightens the coupling. Work in 1961 on high-temperature thermoelectric materials linked conversion efficiency and operating temperature directly to material stability and to radiator requirements. In other words, chasing better conversion changes your thermal problem. It can raise performance or it can increase stress and mass. You cannot optimize one piece in isolation. Now move from physics to product. The biggest uncertainty is not orbital insulation. Sunlight in orbit is steady and plentiful. Uncertainty lives in delivered power that is dispatchable, safe, and bankable. Losses stack up: photovoltaic or thermal conversion losses, power conditioning, transmission losses, pointing losses, reception losses, and curtailment once you touch a real grid. Power quality is also not guaranteed. A 1978 analysis showed output power varies with orbit geometry and illumination conditions. That variation is not just an engineering nuisance. It changes how a grid values the energy and what kind of contracts you can sign. If delivered power ramps, dips, or drops during handovers, the buyer is not comparing you to a solar panel. They are comparing you to firm generation, storage, and grid flexibility services. Because of that, the analytical focus has shifted. Instead of a single monolithic solar power satellite, more recent work treats orbital solar as a constellation and a governance problem. In 2024, researchers modeled orbital capacity and maximum potential energy output for a constellation. That framing forces a new question. How many platforms can occupy useful orbits before collision risk, interference, station-keeping burden, debris exposure, and coordination limits become binding? The ceiling may be set as much by traffic management and spectrum coordination as by engineering. Security and control are now first-class requirements, not add-ons. A 2025 constellation concept called Zeus emphasized secure and sustainable energy transmission. That emphasis is telling. Any system that beams power or even directs concentrated energy will be treated like critical infrastructure. It needs fail-safe pointing, controlled side lobes, verifiable shutdown behavior, and strong cyber-physical security. It also needs an answer to a simple governance question. Who has shutdown authority if something mispoints, interferes, or is compromised. There is also a quieter, potentially nearer-term pathway. Partial architectures. Instead of generating electricity in orbit and beaming it down, you can test pieces of the stack. In 2025, a region-specific concept proposed satellite-based reflectors to route extraterrestrial solar energy for solar power generation over India. Reflectors shift the problem. They may reduce some mass and conversion complexity in space while increasing control, safety, and ecological questions on the ground. Yet they can still exercise key capabilities like precise pointing, orbital operations, and long-duration governance without claiming baseload electricity from orbit. When you translate all this into investment logic, orbital solar becomes three different products. In space power, where the customer is a spacecraft, a lunar facility, or an orbital industrial site. Resilience power, where the customer values independence from terrestrial fuel logistics, weather, conflict exposure, or local grid outages. And commodity grid electricity, where your competition is the future cost of terrestrial solar plus storage, advanced nuclear, transmission expansion, and grid flexibility. Most near-term reality sits in the first two categories. Remote, resilient, military, or disaster response loads can justify higher prices. Commodity electrons are ruthless. They punish variability, complexity, and long development cycles. They also improve every year as terrestrial technologies compound. So what should serious leaders do now? Gate the field with measurements, not renderings. Demand mass per delivered watt, not just mass to orbit. Demand radiator mass and area, not just panel efficiency.